Hi, my name is Jameson Ebert, and I am a PhD student at Texas A&M University. The title of this paper is A Hybrid Approach to Coded Compressed Sensing, where coupling takes place via the outer code. This paper was written by myself, Vamsi Amalladinne, Dr. Chamberland, and Dr. Narayanan. In addition, this material was funded in part by the NSF and Qualcomm Technologies. So to begin, what is coded compressed sensing? In recent years, coded compressed sensing has emerged as a pragmatic scheme for unsourced random access, often referred to as URA. In coded compressed sensing, the URA model is viewed as an instance of a compressed sensing problem, albeit one whose dimensionality is so large as to preclude the straightforward application of standard compressed sensing solvers, such as NNLS or LASSO. To handle the dimensionality of the problem, coded compressed sensing leverages a divide and conquer strategy, where the message payload is partitioned into blocks. Each of these blocks are linked together with an outer code, and then each block is compressed, transmitted, and recovered as a compressed sensing subproblem. After each block or section is recovered, the receiver reconstructs the original message by decoding the outer code. There are two main coded compressed sensing schemes. There's the original coded compressed sensing scheme, which I refer to as CCS, and an enhanced coded compressed sensing scheme, which I refer to as CCS-AMP. CCS and CCS-AMP exhibit the classic performance complexity trade-off, where CCS exhibits a fair per-user probability of error, but benefits from very low complexity, and CCS-AMP exhibits an excellent per-user probability of error, but suffers from high complexity. The goal of this paper is to design a novel coded compressed sensing scheme that achieves the performance of CCS-AMP while maintaining low complexity. In order to achieve this goal, we need to dive a little bit deeper into CCS and CCS-AMP. We begin with the original CCS scheme. In CCS, each user's message is partitioned into L blocks. The blocks are encoded with a tree code, where parity bits are appended to the end of each section. Then each parity encoded section is converted into a sparse index vector and then compressed and transmitted over the multiple access channel. The receiver is then tasked with two things. It must perform compressed sensing support recovery and recover the transmitted sections. Then it must stitch together the sections to recover the original message. To perform the inner decoding or the support recovery, NNLS or LASSO is employed. The outer decoder is a simple tree code, and it connects parity-consistent blocks across slots to reconstruct the original message. And it is pertinent to note that the inner decoding, or the support recovery, and the outer decoding, or the tree decoding, are performed completely independently of one another. On the other hand, enhanced CCS, or CCS-AMP, encodes each section with a rate R non-binary LDPC code. In addition, based on an observation by Thengler, Jung, and Kerr, the L blocks can be jointly compressed using a dense sensing matrix A. This is important because it induces a form of spatial coupling across blocks, and this spatial coupling will become very important in just a minute. At the decoder, approximate message passing, or AMP, is used for support recovery. Within the AMP iterate, the AMP denoiser runs one round of belief propagation on the outer factor graph. This ensures that AMP converges to a parity-consistent solution and also makes the job of message reconstruction a lot easier. Furthermore, running belief propagation within the AMP denoiser induces a second form of spatial coupling across blocks. This will become really important in a minute. After AMP converges, the soft output from AMP is used as inputs for the LDPC decoder. So let's summarize where we're at now. With CCS, the compressed sensing encoding is performed independently on each block, whereas in CCS-AMP, compressed sensing encoding is performed jointly across blocks. In CCS, support recovery and message reconstruction are independent problems, whereas in CCS-AMP, soft information is shared dynamically between this inner decoder and the outer decoder. And the results are striking. the per user probability of error of CCS AMP is much lower than that of CCS, while CCS requires much less memory and is computationally simpler. There is one key observation that can be made though, and the key observation is that CCS AMP employs two forms of spatial coupling across blocks. The first form is induced at the transmitter when the L blocks are jointly compressed using a dense sensing matrix. The second form of spatial coupling is introduced at the receiver when belief propagation is run within the AMP denoiser. It is clear that the complexity of CCS AMP can be substantially reduced by removing either form of spatial coupling. The question remains, though, how would removing either form of spatial coupling affect the per user probability of error of CCS AMP? Based on these observations and this question, we introduced two new coded compressed sensing schemes. We introduced CCS AMP without BP. This is CCS, except that the AMP denoiser does not run belief propagation within the AMP iterate. Instead, the AMP denoiser uses uninformative priors. The second scheme that we introduced is CCS hybrid, which we view as a hybrid between CCS and CCS AMP, because the message sections are compressed independently in CCS fashion, and decoding is done in CCS AMP fashion, where belief propagation is run within the AMP denoiser. We will now compare the complexity and the per user probability of error of both CCS AMP without BP and CCS hybrid. The chart that you see now is the per user probability of error of the original CCS scheme, CCS AMP, and our two new schemes, CCS AMP without belief propagation and CCS hybrid. From this graph, it is clear that CCS AMP without belief propagation performs about as well as the original CCS scheme, while CCS hybrid performs about as well as CCS AMP with belief propagation. As we consider the complexity of the two new schemes, we see that both schemes have roughly the same complexity, which is significantly lower than the complexity of CCS AMP. Based on these observations and these results, we conclude that the spatial coupling induced by running belief propagation within the AMP denoiser is sufficient to harness the benefits of spatial coupling within CCS AMP, whereas merely jointly compressing each section at the transmitter is not sufficient to harness the complete benefits of spatial coupling within this scheme. We thus conclude CCS hybrid nearly achieves the per user probability of error performance of CCS AMP with significantly reduced complexity. This conclusion has several very important implications. The first is that only the length of a single block of the sensing matrix is constrained. This directly enables this algorithm to be applied to much larger systems, even to systems with payloads greater than 512 bits. Furthermore, only one block of the sensing matrix must be stored in memory. In situations where the memory of the transmitter is constrained, this could be very, very important. Additionally, the complexity of message compression is reduced, and it only scales linearly with the number of blocks. These results also show that the weak form of coupling induced by the AMP denoiser is sufficient to harness the benefits of spatial coupling. This opens the door to further research into optimal outer codes for coded compressed sensing. To conclude, in this talk, we've introduced a novel scheme called CCS hybrid that achieves excellent performance while maintaining low complexity. In CCS hybrid, the width of the sensing matrix A is not constrained, allowing its application to scenarios of previously intractable dimension. Finally, we observed that the coupling induced by CCS AMP's denoiser is sufficiently strong to harness the benefits of spatial coupling within CCS AMP. If you're interested in learning more about this scheme, we invite you to come to our poster presentation. We'd love to meet you and discuss the scheme a little bit more, but thank you so much for paying attention.